first step in the derivation is, well, we're going to look at what happens to the solution, this solution, when t is equal to t1. Then we're going to look at what happens to the solution when t is equal to t2. So we need to substitute t is equal to t1 in this equation. We need to substitute t is equal to t2 in the equation. What I'm first going to do is I'm going to look at the sine function, just the sine function, when t is equal to t2. So I'm going to look at sine of omega d t2 plus phi. And I'm going to try and relate this to the value of this thing when t is equal to t1. Now what I know about t2, if I want to relate it to t1, is that the distance between t2 and t1 is equal to tau d. Is the frequent distance, the period. So t2 is equal to t1 plus tau d. Tau d is 2 pi divided by omega d. So sine omega d t2 plus phi is equal to sine of omega d times t1 plus 2 pi over omega d plus phi. Now, inside the sine function, I'm going to expand the brackets, so I get sine of omega d times t1 plus omega d times 2 pi divided by omega d. Well, omega d times 2 pi divided by omega d is 2 pi plus phi. Now if I have a sine of an angle plus 2 pi, well, 2 pi means I go around the circle once, around the whole circle. So sine of alpha plus 2 pi is just equal to sine of alpha. Sine of alpha plus 360 degrees is equal to sine alpha. So this whole thing is actually equal to sine omega d t1 plus phi. Okay, now this is basically the first and already the most important step in derivation. To look at. The next step is, I'm now going to look at the ratio of two peaks. So I'm going to look at x1 divided by x2. Now, I know that x1 is the value of x when t is equal to t1. And x2 is the value of x when t is equal to t2. Up there, I have the general form of x at time t. So c exponential minus theta omega nt times the sine of omega dt plus phi. And just to get xt1 and substitute t is equal to t1, to get xt2 I substitute t is equal to t2. So if I substitute t is equal to t1, I get c exponential minus theta omega n t1 times sine omega d t1 plus phi. So that's x at time t1. The bottom, x at time t2 is equal to c exponential minus theta omega n times t2 times the sine of omega d t2 plus phi. Okay, now compare the two. I get a C, both the top and the bottom. So these two C's cancel. Then at the top I have sine of omega d t1 plus phi. At the bottom I've got sine omega d t2 plus phi. And up there, I've just concluded that sine of omega d t2 plus phi is just equal to sine of omega d t1 plus phi. So also these two terms cancel. So what remains is just these two things here. What remains is the exponential of minus theta omega n t1 at the top, exponential of minus theta omega n t2 at the bottom. Are there any questions? Okay, so if I rewrite this, I got exponential of theta omega n. Well, I have the exponential minus theta omega n t2 at the bottom. If I take that to the top, I can do that by putting an extra minus sign to the exponential. So if I bring it to the top, I get exponential plus theta omega n times t2. So I have exponential of theta omega n t2. At the top, I have exponential of minus theta omega n times t1. So it simplifies quite a lot already. Next, realize that t2 minus t1 is the distance between t2 and t1. And the distance between t2 and t1 is just this period toward t. So this is equal to the exponential of theta omega n times toward d. And what I know about tau d is that is equal to 2 pi. Well, let's just move step by step. I was just going to make a bigger jump, but tau d is equal to 2 pi divided by omega t. Okay, next step, substitute what you know about omega d. So I get omega d, omega n times 2 pi, and omega d is equal to omega n times the square root of 1 minus theta squared. Any questions?
You missed out the coefficient, the damping coefficient.
Theta, okay, yeah. theta arm again, 2 pi over omega d. Any other questions? Okay, got an omega m in the numerator and an omega m in the denominator. So what remains now is that this is equal to exponential of 2 pi theta divided by the square root of 1 minus theta squared. So what you find now after this derivation is that this quotient of 2 consecutive peaks only depends on theta and not on omega n. It's only theta that determines what is known as the decrement, so the ratio of 2 consecutive peaks. And that allows you now to just reverse this. I have expressed x1 divided by x2 as something which depends on theta only. I'm now going to turn it around and solve theta from this. Because x1 divided by x2 can be obtained from an experiment by just looking at the behavior of the system. For this, rather than looking at x1 divided by x2, so the decrement, we're going to look at what is known as the logarithmic decrement of the behavior. So I'm going to look at the ln of x1 divided by x2, and this is normally called delta. So if you see delta, looking at vibrations, this refers to the logarithmic decrement, the logarithm of the ratio of 2 consecutive peaks. So delta, well, if I take the ln of an exponential, I just get the argument. So ln of x1 divided by x2 is 2 pi times theta divided by square root of 1 minus theta squared. And now, what I'm going to try and do is solve for theta. First step, I don't like denominators, so I get rid of the denominator on the right hand side. So I multiply everything by the square root of 1 minus theta squared. So I have delta times the square root of 1 minus theta squared is equal to 2 times pi times theta. Second step, I don't like square roots, so I square everything. So if I square everything, I get delta squared times 1 minus theta squared is 4 times pi squared times theta squared. The third step now is I want to solve for theta. And I know the whole expression is involving theta squared only. So in the first instance, I'm going to solve for theta squared. And to do that, I need to make sure that everything involving theta squared is on one side of the equality sign. So if I take this minus delta squared times theta squared to that side, I get 4 pi squared plus delta squared times theta squared is equal to delta squared. And now divide everything by 4 pi squared plus delta squared, and you find theta squared is equal to delta squared divided by the square root, no, not yet, not square root yet, divided by 4 pi squared plus delta squared. And then the last step, I want theta, not theta squared. So take the square root of everything. So I get theta, the square root of delta squared, which is delta, divided by the square root of 4 pi squared plus delta squared. So, in an experiment, if you want to know your damping ratio, what you do is you set your system in motion, you make sure that you have an appropriate measurement system using a laser, for example, which allows you to record consecutive peaks. You calculate the ratio of 2 consecutive peaks, calculate delta, so you take the ln of this ratio, and then this formula just gives you the damping ratio, without having done any modeling on the system, trying to find exactly the parameters, the mass, stiffness, etc. in the system. Now once you know theta, and you have recorded the period of the vibrations, so you've recorded tau d, which means that you know omega d, well then you know that omega d is equal to omega n times the square root of 1 minus theta squared. So if you would be interested in omega n, you just take omega d divided by the square root of 1 minus theta squared. Well, again, omega d can be obtained from the measurements. It's just timing the distance between two peaks. And your theta you have obtained from your logarithmic decrement. So you see, theta and omega n can just be obtained by taking appropriate measurements on your vibrating system. Are there any questions? Okay, let this sink in. Tomorrow I'll get back to the derivation, go through it again, and also do an example of showing how you would use this in practice. Before everyone starts packing, now start with the next topic. You need to get your money's worth if you pay a lot of money, don't you? So I'll just and I get the feeling that I am working for my money. So
यही वैल्यू है ना, हो जाएगा उसमें 175 वैल्यू है ना, ये देख ये इस तरह आंसर आ जाएगा। 175 पे पीक्स है ना, दो सब्जेक्ट पे। क्वेश्चन 7 हो गया।
ये कौन से सवाल कौन से फॉर्मूले से?
आखिरी वाले में, ये वाले है डी स्क्वायर। नहीं इस बस ये यूज़ कर पता तो है ये।
We have so far looked at 3 vibrations of systems. Now, if you remember the video, one of the videos we start off, all of the videos we start off with, when we started looking at vibrations, all of these dealt with what is known as forced vibrations, or in other words, vibrations where there is still an external force acting on the system. And normally in practice, that's what you normally encounter. And these forcings are normally what cause the problems. particular what is known as resonances cause the problems. So what we're going to look at is the forced response now of systems. So we're going to assume that there is some force acting on a system. Well, there were in the videos there were some forces acting on the system. In the first place, the helicopter, it was vibrations due to imbalance in the rotors, which was an external force. The Millennium Bridge, it was caused by the people walking over the bridge. The Tacoma Narrow Bridge was oscillation or forcing caused by the wind going, or wind forces around the bridge. Now, there are kinds of, all kinds of input functions that would normally be looked at in applications. The most important one, as we will see later, is, and that's the one we will be concentrating on, is harmonic forcing. So sine or cosine forces acting on the system. The reason why these are the most important forces is, in the first place, that if you are just given a system and you're asked to describe the system and to figure out some properties of the system, what you normally do is carefully measure the response while you're putting in harmonic forces at different frequencies. Now, if you know the response to harmonic forces at different frequencies, basically there's a mathematical theory called Fourier theory, which tells, which I will say something about, a little bit about later on, which tells you that actually you know the response to any possible forcing. So if you know response to harmonic forcing, then actually you know almost everything about the system. So that's why this harmonic forcing is so important, and why we will normally be mainly looking at that. Okay, so I don't know why I've got this up actually, because I don't need that. I'll just do things on the board again. Of course, we were told in the questionnaires that you don't want lecturers to read from the notes, so won't be doing that. So when I look at my simple mechanical system again, 1 degree of freedom, x double plus 2 theta omega n x dot plus omega n squared times x. Earlier on in the free vibrations, free behavior, we looked at the right hand side equal to 0. We will now be looking at the right hand side, which is not equal to 0. So we have some external force acting on the system, which is represented by some function u of t, which is not equal to 0. Now, if you go back a long way in the module where we looked at characterization of differential equations, we looked at linear differential equations and we separated them into homogeneous and non-homogeneous differential equations. The homogeneous ones were the ones defined as differential equations where there is no term that depends on the independent variable only. So homogeneous differential equations don't have any terms depending on the independent variable only. In this case, the independent variable is t. What you see here, well, there is a term which depends on the independent variable only. So this is not a homogeneous differential equation. This is an inhomogeneous differential equation. I now want to look at, in general, how you would try to solve an inhomogeneous differential equation. And actually, it turns out that if you want to solve an inhomogeneous differential equation, you have to take 2 steps. you solve the homogeneous differential equation, and you find only one solution to the inhomogeneous one. If you combine the two, you get a general solution of the inhomogeneous differential equation. Just to show that, let's assume that x1 and x2 are both solutions to this differential equation. So I assume I have found two solutions to the differential equation. And that means that ut, so if x2 is a solution, then u is equal to x2 double plus 2 zeta omega n times x2 dot plus x plus omega n squared times x2. That is what we mean by a function being a solution. It satisfies the differential equation. So if I apply this recipe to the function, take the second derivative plus 2 zeta omega n times the first derivative plus omega n squared times the function itself, it has to be equal to u. That's what I mean by a solution. Secondly, if x1 is also a solution, the same should hold for x1. So u should also be equal to x1 dot plus 2 zeta omega n times x1, so x1 double here, plus 2 zeta omega n times x1 dot plus omega n squared times x1. So if x1 and x2 are both solutions, which are not necessarily the same, then these two equalities should hold. So what I'm now going to do is I take these two equalities and subtract them. So if I subtract the top, the bottom from the top, the left hand side I get u minus u, which is 0. Then I get x2 double minus x1 double on the right hand side. So see, I get x2 double minus x1 double. For the second term, they both have 2 zeta omega n. So I write down the 2 zeta omega n. Here I have x2 dot. And there I have, bottom I have x1 dot. Finally, these two terms, then omega n squared, then omega n squared here, so I have omega n squared. Top I have x2, and I subtract x1. So what you see is if I say, I call x2 minus x1, I just give it a different name, I call it xh. Then this thing here is xh dot. Because if I take the derivative of difference of functions, it's the difference of the derivatives. And this thing here is xh double. So x2 minus x1 is equal to xh, which means that x2 t is equal to x1 t plus xh t. where I have that xh double plus 2 theta omega n. xh dot plus omega n squared xh is equal to 0. Now, this is basically the basis for looking at solutions to these non-homogeneous differential equations. Because what you see, if you imagine I have one solution to the inhomogeneous differential equation, x1, and I would have another solution, you can always write the other solution as x1 plus function xh, where xh is the solution to the homogeneous differential equation. Hence, using xh. Yeah, so any solution to the differential equation can always be written as another solution plus a solution to the homogeneous differential equation. Which means that if you want to find a general solution of the differential equation, you just solve the homogeneous differential equation. So you find a general solution to the homogeneous differential equation. You find only one solution, which is normally known as a particular solution to the inhomogeneous differential equation. Add them together and you have characterized the general solution to the inhomogeneous differential equation. So basically you only need to solve this inhomogeneous differential equation once. So that's the first thing for these differential equations. Now, a second, even nicer thing is the following. If we are looking at vibrations, etc., we're normally interested in the long-term behavior of solutions. We're not interested in what happens initially, we're just interested in what happens in the long run, when the system settles down in some kind of vibration or whatever, which is what we express as saying we are interested in the steady state behavior. What we have just seen for solutions to this homogeneous differential equation is that they always die out. They always go to 0. So in the end, these terms always go to 0. And any solution, any other solution than the xp or the x1 you found, will start to look the same as just this one particular one you found. So in the long run, you're not even interested in what happens here. You are just interested in finding one solution to this inhomogeneous differential equation. And you know that even though solutions might differ initially, in the end they will all look the same. So in the end, you will always have a steady-state solution, whatever your initial conditions are. So in the end, for practical purposes, if you're interested in long-term behavior, you only need to solve this thing once. So if by any chance you just happen to see one solution, you know it's enough in the long run, because everything else will look like that solution. Basically, that's then the starting point for what we are going to do next when we look at frequency response. So when we look at what happens when we just put a harmonic function into the differential equation, we're not going to look at any possible solution, we're just going to try and find only one. And we know that in the long run that's enough, because this part here is always going to disappear. Are there any questions? So I'll let you off now.